are saying an example to try out the Spearman's rank correlation coefficient. And we're establishing, we are analyzing this data that is telling us that a student studied for a number of hours and scored a particular score in a subject Y. So we are saying we are going to use either the Spearman's rank correlation coefficient or the Pearson correlation coefficient to establish if to establish the level of association of the number of hours vis-a-vis the score a student attained after studying for those number of hours. So you can look at it and please go ahead and try it. Because here you'll need to, for example, you'll need to get the rank. Let me show you what you need on your table. So you need that number of student, maybe student. Then you need the X. You need the rank of X. Okay. Then you need the Y. Then you need the rank of Y. Okay. Then from there you need the D. Okay. Then you need the D squared. D itself is the difference between the rank of X and rank of Y. And it doesn't matter whether you get the rank of Y minus rank of X or you get rank of X minus rank of Y. At the end of the day, when you square, if there was a negative, then that negative would vanish and you would still get the same answer as if someone did it the other way around. And therefore, the Spearman's rank correlation coefficient will be 1 minus 6 sum of D squared divided by N into N squared minus 1, as we had earlier on said. Then from there, you can go ahead and comment basing on the value of R. I mean the value of rho, the Spearman's rank correlation coefficient you have obtained. Then you can also do the same for Pearson correlation coefficient. So here, we shall need to determine the sum of the values divided by their number. So here we are trying to use this formula, which is equal to R is equal to sum of X minus X bar into Y minus Y bar. So you get X bar, which is the mean of X values. Then you subtract from each value of X, you subtract this mean. That means you will have 2 minus this 5, 3 minus this 5, 7 minus 8 minus that. Then also get the mean of Y values. So the Y values are also here, meaning that to get this one here, you will be getting 50 minus 73, 60 minus 73, 90 minus 73. Then from there, you are going to sum. You multiply the 2 and then sum. Maybe let me put the headings of your table. I could be having a student. Okay. Even if you don't put that student, it doesn't matter. But you need to have X. Okay. You need to have X minus X bar. You need to have Y. You need to have Y minus Y bar. You need now to have you need to have X minus X bar. Remember, this R is supposed to be that one over square root of X minus X bar. We are supposed to sum here. So we are supposed to sum of X minus X bar squared times the sum of Y minus Y bar squared. Everything is under root. So that means here you need X minus X bar squared. You need Y minus Y bar squared. Then you obviously need also the x minus x bar into y minus y bar. So you put those values here, you put those values here, you put those values here. Later on, you substitute in this r, and you'll be able to get the value of r, which is the Pearson correlation coefficient. So for us, the mean is given as that, and that is 5. Here is 73. We have calculated that. So this is what we are talking about. You do your table like that. Okay. I'm not calculating this because we had earlier on reviewed this. So it's yours to try out and see that you get the values that we are getting down here. Then this one is, we are calling it the sum of the products. Okay. And others call it the covariance. Okay, the covariance between x and y. Then you sum the squared differences. The squared differences obviously are here. Okay, the difference is here, so its squared is here. The difference for this y is here. Its squared value is here. So you try it and make sure that later on you substitute in this formula and get this value. So the interpretation for the result is telling you that there is a very strong positive linear relationship between hours studied and exam scores. So as the number of hours studied increases, the exam scores tend to increase as well. And this relationship is very close to being perfectly linear. So that means if I plotted a graph between the two, I would find that I'm coming up with a perfectly linear graph. Now, we also talked about regression lines, and then today we want to look at how do we get these coefficients, because we have, for example, two expressions whereby we are talking about a graph of y on x, or a regression line of y on x, a regression line of x on y. So you need to determine these coefficients. So one of them, if we are talking about y on x, the regression line will be defined by y minus y bar is equal to b y on x into x minus x bar. That's one. Another one is also going to be defined by x on y. And that x on y is also telling you that you have x minus x bar is equal to b x on y into y minus y bar. So these two expressions that I'm giving you here help you to determine the coefficients. These coefficients are what we also called, this is the coefficient of y on x. This is the correlation coefficient of x on y. And they are very important in defining the equations for these regression lines. So for this one, you can have an equation of x equal to, for example, bxy times y plus maybe a constant k. Then this other one will also be, let me change color here. This is going to be y is equal to byx. Of course, we are saying is the correlation coefficient of y on x times x, then plus also maybe a constant k1. Maybe this is k2. Okay, just arbitrarily assigned. So these are the lines. This line is actually a straight line, but it is telling you it is a line that is expressed in terms of it is y expressed in terms of x. So we are calling it a regression line of y on x. This is a regression line of x on y. You have to understand that. So from these coefficients that we are putting here, you are able to determine the Pearson correlation coefficient. So sometimes you are not given that data above. You are not given this data, but you are given lines with expressions. You could look at them as simultaneous equations, but they are representing regression lines. And from there, they ask you to determine the Pearson correlation coefficient. So what we are doing here helps you to determine the correlation coefficient of Pearson for those regression lines. And also, when you look at, for example, Byx, that is the correlation coefficient of y on x, is equal to r, which is the correlation coefficient, times standard deviation of y divided by standard deviation of x. And the correlation coefficient of x on y is equal to a Pearson correlation coefficient times the standard deviation of x divided by standard deviation of y. Good. So if we have understood that, they are, of course, named here. And then we go ahead to determine what we call the correlation coefficient. Correlation coefficient is already given by this formula. This one is the same as what we already had above, as x minus x bar into y minus y bar divided by the square root of, this is standard deviation of x. The standard deviation of x is the same as x minus x bar. Let me put the sum. Sum of x minus x bar squared. Remember, what is inside here is variance. So if we take square root of variance, we get the standard deviation. So times the square root of, you sum y minus y bar squared. So this one is also the standard deviation of y. So when you see this formula, R is equal to covariance between x and y divided by standard deviation of x times the standard deviation of y, no, it is the same as this. Now from there, we are defining now the correlation coefficient of y on x. It is given by the covariance between y and x divided by the standard deviation of x squared, or divided by the variance of x. So that is covariance between x and y divided by the standard deviation of x. This one is also equal to the covariance between x and y divided by the standard deviation of y. Okay?
What about that square?
Okay. Maybe this is squared, isn't it? So maybe let me change that one to be the variance. Because when we have Let me change it to be variance divided by the variance of x, variance of y. So that if I take the square root of this variance, I get the standard deviation. So thank you for that check. So now that one is okay. That one is now okay. So expressing regression coefficients using R, we have already done that. So our task is to, for example, get the covariance out. So from any of these, for example, from any of these, let me show you something. So we already said our R, is equal to covariance between x and y divided by sigma x, sigma y, divided by sigma x, sigma y. So meaning we can get the covariance of x and y equal to sigma x, sigma y times r. And we can call that one an equation. Then it is from that we can also say from the correlation coefficient of y on x. So we have byx equal to covariance between y and x divided by sigma y squared. If that is the case, we also get covariance. So covariance between y and x will therefore equal to sigma y everything squared times byx. So is there anything you see related? Maybe this is double star. So if you see anything related above, you tell me, because you see this and that are the same, so I can equate this and the other one. So what happens is that I will have sigma x, sigma y, r equal to sigma y squared times byx. So this and that can go. So if it goes, in other words, I can say divide both sides by sigma y. So if I divide here by sigma y, that square will go, but I will maintain a 1 sigma y. So what will be r? R will therefore equal to sigma y divided by sigma x times byx. Yes. But also, if I now use bxy, this would be covariance of between x and y divided by sigma x squared. And what will be r?
But I'm not seeing anything on my screen.
You are not seeing anything.
On my screen. Okay. Yeah, it's okay then.
Okay. So r, if we are talking about b, xy, it will be covariance of x, y divided by sigma x squared. And this r would therefore be sigma x divided by sigma y, bxy. And that would be another definition for r based on correlation coefficient of x on y. So that's what you can see that is being obtained here, and that is the same. And that is the one we are talking about. So you can again use that problem, and then you'll be able to, for example, get the model that maps or that states the relationship between these two. We have hours studied and exam score. This is another example that we are looking at. But here, we want to generate a model that is, for example, in terms of y is equal to, for example, maybe b times x. Okay, those models are in form of y. Y is equal to, for example, a plus bx, whereby b is going to be the slope of this graph, and a is going to be the y-intercept, or the value of y when x is equal to 0. That is a. If I have a graph in terms of y and x, so if I plot this line, and it is like this, b is going to be the slope of this graph, but then at this point where this line cuts the y-axis, when x is equal to 0, is going to be represented, or is going to be determined by a. So from here to there, it's going to be a. So now, talking about this problem, you are going to see that we need to generate a model, and later on, we use some data to predict the outcome of the model. And that is the essence of regression analysis. So we have the number of hours of student study, then their scores. So one, we need to determine the means of x and y, because they are going to be very important, especially when determining the correlation coefficient. Okay, so when you determine the mean, you sum the number of hours divided by the number of data points, and you get 3.5. Then y bar, you also sum all those divided by their number, then you get the mean score. Now, you calculate the regression coefficients, and that is going to be b and the intercept a, because our equation is y is equal to a divided by bx. So we are calculating for a, we are also calculating for b. To get b, we need to use this formula. And this formula, we said, this is the covariance between x and y divided by the standard deviation, the variance. It can be the standard deviation x squared or just the covariance. So we proceed. This covariance between x and y, this is how we get it. You get each data point, subtract the mean of those data points, you multiply by the y, each of the data points of y minus their mean, then you do the multiplication. So after the multiplication, you sum. Remember, you have a data point for maybe student A, B, C, D. So each of these, you are supposed to determine this xi minus x bar times y minus y bar. You write there. That product, you write there. That product, you write there. Then you determine the sum. Okay, so after determining the sum, you'll be able to get also the sum of these, then you will calculate for b. So we have already determined the mean of x and y, and that is our graph. So xi minus x, you write here. For y, you also write there. The other one, the product that would lead us to the calculation of the covariance, you also write it there. Then the variance of x, you write it there. Then from that point, you sum, you get these points. You get in 119.0. For this, you also get 17.5. So this is the sum here is equal to 119, and the sum here is equal to 17.5. That's what we are talking about. Then to calculate the slope, you get this divided by that. So you have 6.8. From there, to get the intercept. So to get the intercept, we are going to use the mean values of this analysis. The mean values of x, the mean values of y, and substitute in the equation y is equal to, we say the a plus bx. But now the values of x we are going to use are going to be the mean. The values of y we are going to use are going to be the mean values of y. Then from there, we make A the subject of the formula. If we make A the subject of the formula, this is going to be y bar minus b x bar. We have already calculated for b, x bar we know it, y bar we know it, and that is going to be our A. So we are going to develop the model by just writing our general format and then substituting the values for A and the values for A and that one for B. And now that will be our regression model. So now you can make predictions. The interpretation is that for every additional hour studied, the exam score increases by approximately 6.8 points. That is the slope that we are talking about. Okay? That each hour studied, the score increases by 6.8. Yes. So then the intercept is 42.87 and represents the expected exam score if no hours are studied. So if the student did not study in any way, like he did not spend any time in class, his expected score around this. So obviously is less than 50, and this student is likely to fail. That's what the model is telling us. Then we make predictions. If a student studies for 4 hours, the predicted score is going to be, so where there is x, the number of hours, we put 4. And that will be 42.87 plus 6.8 times 4. And the value is going to be 70. So this student is going to pass highly with a 70%. So this regression model provides a simple linear relationship between hours studied and exam scores, allowing predictions based on the input variable x. Before we entertain questions, let's look at measuring the accuracy of this model. And we measure the accuracy of this model by using the coefficient of determination. Coefficient of determination.
Excuse me, sir.
So we are saying the coefficient of determination helps us
Excuse me. Yeah.
proceed. Now we are saying this is our regression model that maps this data very well, and we have said this is the A value, which is giving us the y-intercept, or the value of y when x is 0. In other words, if we are talking about that x is the number of hours studied, so when the student did not study any, he did not attend class or studied for any amount of time, then this is his expected score in the subject that is being talked about. And then finally, that's what we are able to get given the above data. And then we are saying we need to measure the accuracy of the model by using the coefficient of determination r squared. And now what is r squared? R squared measures the proportion. We are saying R measures the proportion of variance in the dependent variable y that is predictable from the independent variable x. The value lies between 0 and 1. If r squared is equal to 1, the model explains all the variability of the response data around its mean. And if it is 0, the model explains none of the variability of response data around its mean. Then r squared can be determined by that. So r squared is equal to 1 minus sum of y minus the predicted value of y, then we square, then divided by sum of the variance. So variance itself. This is the variance of the response or the variance of the y values, whereby this y is the predicted value of y. And once you have the predicted value, then if I get 1 minus this component, then that r squared that I will get will be the coefficient of determination. There are other methods for measuring the accuracy of the model. We have the mean absolute error, the mean squared error, root mean squared error, adjusted r squared, residue analysis. So those others, we shall not talk about them. Even r squared, we are trying to basically look at how we can measure using a basic method. But we may not go into details of that. But given any question to determine the root mean square error value, then those models or the formulas or the expressions have been given here. So how do we choose the right metric or the one parameter to measure the accuracy? We need to look at r squared because it is for overall model fit, or is the one that tells us that this model fits the data very well and is the most commonly used. For predicting the accuracy, then the root mean square error and the mean absolute error values are very important for predicting the accuracy. Then for comparing models, we will need to use the adjusted r squared and then the AIC stroke BIC, which is the archaic stroke Bayesian information criterion. And these ones, we shall not use them. But we are just trying to highlight to tell you that in any case, if you go deep into measuring the accuracy of these models and also determining whether these models are able to do what you're intending to predict, these are the metrics that you're going to rely on. So using our example above, the example above that we got here, we are able to determine r squared and then be in a position to talk about the accuracy of our model. So we are saying that r squared will be equal to 1 minus sum of, say, the y minus y predicted divided by that sum of y minus y bar. So the predicted values are obtained by putting x values in the model. So here we said we have y is equal to 42.87 plus 6.8, 8x. So we have the equation is equal to 42.87 plus 6.8x. So what we do, you look at each value of x, maybe 1, 2, 3, 4, 5, etc. Substitute them here and get the values of y. So the y that you're going to get is going to be this kind of y. Then later on, you use that formula and be able to determine r squared, which will be the coefficient of determination. So before we go any further, I need any questions, then we'll proceed.